Hello. Should I use my sound?
Mute yourself there. I guess I can probably do a few words into the okay. Maybe you can give it a few moments. Yeah. Is there any other people coming from? Yeah, I have a few people here, not as many as last year, maybe, but yeah, so I should move out. Super. So 6 4. No giving talks. I gave one earlier this morning. Okay. And then there's a few oral papers, but I'm not presenting. Okay. I'm just stealing from oral supply. In the venue, it's always, I mean, on the fourth floor, it's always hard to find because most of the rooms are on the third floor. That's right. Yeah, that's always the trouble with the two floor setup. Yeah. Is there a lot of people joining the challenge and the challenge? So we had basically just one team that managed to get a successful policy. And we had a few other teams that tried. I think it will take a little bit more time to actually get a reasonably successful policy. I think is it for like they are not familiar with the infrastructure, or I think for many people it's probably the first time training a policy on the early system. Okay, so I guess it's on. And actually it's that get familiar with how training policies and full knowledge of actual hundreds. Okay, so the data is so the setup is mostly drawing. Yeah, so the robots are really validating on this one. Okay, you can of course train on whatever you want, but probably it's helpful to train on drawing. I see. Yeah. We actually have train on drawing, and it does. It's not easy to train on drawing because there are a lot of freezes. Yeah, so you need that. Okay, I see. Yeah, we released our baseline implementation for the process I trained, and we also have to add the implementation as part of that. And it is important to have that. I see. Under the policy. Yeah, or you get stuck if they don't have money. Yeah, yeah. Yeah, that's probably why we didn't get really work. Should try again. I think with our open source idle filter should be. Okay. Is it really the idle filter? Is there any other tricks? Not much. Like I'm sure you can get much better performance if you apply new tricks. Okay. Like what's what you have there now is basically just a lot. Policy. Yeah, I guess it doesn't matter that you have an architecture that's like expensive. And scale to that sense.
So this one is there like ISO 0.5, 19
Yeah, that's currently the best one. There. But they also train from college and also.
Okay.
Like you don't need to zero pre-train to get a decent ones.
How big is the difference between
Like in our advisor website, there's a notable that is 450 versus not. There was not that.
I see. So how many distributed sites does the RoboArena have?
So we started with 7. I think we maybe added 1 or 2 more since. One of which is in China now. The Protobot guys just are running evaluations at no. The company is called Robots. They did like some navigation thing before.
Oh,
Michael Cho.
I know him. Yeah, I know him.
So his company is, I guess, running a few units.
Okay,
I see. Set up.
I see.
Continuously
I see. Wow.
Yeah, and then in the US,
Okay.
okay.
So do you have an estimate for how long the will has to run in order for you to have some confidence to install significance?
I thought policy.
Yeah, I thought previously you said like around 1 month or around 1 month.
Oh, I think it can be quick. Like I think you probably need like maybe 50, 60, 70 pairs of those to get a good like policy ranks.
Okay.
And when we submit a new policy that hasn't been evaluated much, we're trying to update it into so that it gets settled.
Okay, yes.
So that you can get it. Say if you are started.
Okay.
I can put up the, we are sharing this. All right, cool. Well, thanks everyone for coming. Excited to get our workshop off to a good start. Yeah, I mean, the topic of our workshop is to look at policies in the wild and to look at RoboArena Challenge, which is one way in which we're trying to evaluate the capabilities of these policies. We have 3 exciting speakers today. Yang is already here to get started. In terms of what we're planning for today, it's a half-day workshop, so not particularly long. We'll start with Yang's talk, then we will have a bunch of orals given by the people who actually managed to get a good RoboArena policy and a few of the papers that were submitted. Then we'll do poster session, and then we'll have 2 more talks in the afternoon, and that's it. All right. I assume there are no questions about what we're doing today. Then Yang, if you want to come up, very excited to introduce our first speaker. Yang Gao is a professor at, maybe I should stand on this side. No, professor at Tsinghua, I think also maybe startup founder.
Yeah.
Not on your website, I'm not sure. And has done a lot of great work at the intersection of vision, of manipulation, and a lot of VLA-ish stuff recently. Also in the startup, I think very much robot learning. And so I think he will have a lot of things to say about how to get policies to be deployable.
Yeah.
If you want a clicker, this is a clicker, but you need to.
Then, okay.
This is unmuted. Okay, I think this should be good now.
Do I need to full screen this?
Yeah, maybe you can. Just double click it.
Okay.
Oh, full screen at the very bottom.
Very bottom?
Yeah. Okay. All right. Oh, and if you minimize that.
Okay,
Yeah, I think that's a way.
cool. Yeah, thanks, Carl, for the introduction. It's a great honor to be here to talk about maybe not the most immediate steps to train your policy, but talking about how we can further scale up the policy learning in the future. So the title of today is Scaling Robot Manipulation with VLMs and Human Videos, and some of the lessons we have learned. And I'm Yang, I'm an assistant professor at Tsinghua University. I'm also the co-founder of Spirit AI, a embodied intelligence company doing both hardware and software. Okay, so we all know that if you have ever trained robot policies, we know that teleoperation is pretty expensive and it's very hard to scale teleoperation to the level of the data we have on the internet. So how do we solve this? So today I'm going to talk about one way to solve this. Of course, there are probably many other ways to solve this, but I'm going to talk about one way that is the data is already there and it's only the algorithm that is not there yet. So maybe it's the best of interest to everyone to look at this problem at the current moment. Yeah, so if we want to resolve the lack of data issue from the internet data, one way we could do it is to reuse the large-scale pre-trained vision language models because they have absorbed a lot of knowledge on the internet, and it has done pretty good vision and language grounding. But another source, which is still underutilized, I think, is the internet videos. It's the internet videos of human doing a lot of things, including both egocentric and actual and non-egocentric data. So those videos are kind of having a lot of embodiment difference compared to Robo videos, but they are extremely diverse in terms of the environments and in terms of what people are doing. So I feel like this could be a very good source of pre-training data for the future robot policies. Okay, so how we can use those data? So I look at the existing literatures and vaguely classify them into those three categories. So the first category is we can ask the VLM to explicitly output things that can directly dictate actions for methods such as code-as policies or work poster or COPA. And those methods are directly using those VLMs and outputting actions. And the second one being, let's use those pre-trained knowledge in an explicit manner. For example, many of the great works have done by physical intelligence, such as pi and pi 0 and pi 0 and 0.5, and also the very early work in this trend, the RT2. And the third category is how to learn from those human videos. As I said, there are a bunch of very abundant information on the internet of human doing various things and how we can learn from those. So today I'm going to give an overview about all those three types of methods and what people have done and what's their drawback and what are the future improving directions. So yeah, in this talk, I will talk some about my own past work, but I'll also talk about some of the work of the other people, which are representative works. Okay, so the first category, how we can use the VLMs to directly output actions. So what do we mean by using VLMs to direct output actions? I mean by we can use VLMs to output action by, for example, generating programs, such as code-as policies, and we can use VLMs to generating motion primitives. And we can also be using them to generate constraints on key points so that we can solve some equation of those key points to generate motions. And some example methods including, for example, those code as policies and workposter and COPA and recap. So I'll be talking about one of my past work called COPA, which stands for constraints of parts. So what does it mean? Okay, let's take this example. So if you want to use a hammer to hammer a nail, then if you ask a human to describe how to achieve this task, then a human will probably say, okay, I first need to put a hammer with the hammer's head facing downwards towards the head of the nail, then and make sure they are on the same vertical direction, and then I hammer it down. So that is probably what human will say. And this work, COPA, basically convert that intuition into a bunch of templated spatial constraints. So here, of course, we are assuming some pre-annotated geometric elements on top of this image. For example, we assume we know the surface of this nail and we know the surface is normal, etc. And then we can ask the VLMs to output spatial constraints on those geometric elements. And then we can solve for the optimal pose under those geometric constraints. And then we can use the motion planner to reach those targets and execute the motion. Okay, so that's what we mean by an explicit methods to use VLM to generate actions. And the pros of those methods is that they are typically zero-shot. They don't need any fine-tuning with the models, and they will also inherit the object, scene, and common sense generalizations by those VLMs. And since you don't fine-tune them, so the capabilities of those generalizations won't be lost during the motion execution. But cons is also very obvious. Those type of methods can only do limited type of motions. They couldn't do many dexterous manipulation. For example, if you want this type of method to assemble some IKEA furniture for you, that is probably not possible. It's only able to do simple manipulations. And there is no obvious ways that we can scale those methods to very complex scenarios. So how do people deal with this? I think the most promising direction is to fine-tune those VLMs to a VLA, such as on this page I show a work of Pi 0.5, which is a pretty fantastic work that combines a pre-trained VLM with an action expert and fine-tune on Robo data, so that those VLMs can provide the information of answering what is where, and the Robo data can provide the information of how to move in order to achieve those manipulation capabilities. However, the issue is also pretty severe because the amount of Robo data we can collect is only limited. For example, Pi 0.5 is trained on a vast amount of 10,000 hours of teleoperation data, but that amount is still much less than what we have on the internet. Okay, so the pros of those methods are, in theory, they can complete any motion you would like. And they also inherit the internet scale vision and language grounding information. So that makes it very good at, for example, identifying new objects that has never been seen in Robo data. But they still have the issue of it is very hopeless to collect enough amount of Robo data. Okay, so how to resolve the lack of data issues? As I said in the very beginning, I feel like taking a good use of the internet human videos is a very promising approach. That is because the human videos contains a lot of the motion information, which VLM doesn't contain. So what VLM contain is mostly the object grounding information about what is where. But human videos contains the information of how do I assemble an furniture, and how do I pour water, how do I wash dishes, how do I prepare a meal. So those videos contain a lot of the motion-rich information. And I feel like that is a very good complement to the existing VLM information or VLM knowledge we have. Okay, so yeah, so learning from videos is also a new idea, and a lot of people have investigated some of the methods that are trying to take advantage of those human videos. So today I will briefly review 4 types of algorithms and talk through what is the benefits and drawbacks of each of those approaches. So the 4 types of approaches can be summarized as the first one being using explicit hand and object pose to abstract the human videos. So that is pretty straightforward. If you want to learn from human videos, the easiest thing you can do is you can extract a low-dimensional state representation, which is a hand and object 6D pose. And the second type of algorithm is a little bit more general. It sample a lot of points on the video and track those points movements, and using those points movements as an intermediate representation of the motion in this scenario. So this has the benefits of you can be more flexible on object types. You don't have to define 6D pose. For example, a lot of objects, such as a water bottle, is symmetric, and it's impossible to define a 6D pose on the water bottle. So point tracking is an emerging solution to that problem. And the third type of methods is called latent action models, such as LAPA, which is going one step further, that is trying to say, okay, let's not doing point tracking, let's extract a action embedding. So the action embedding is something very similar to word embedding, in the sense that it is a high-dimensional vector that describes the action, but it's not an explicit representation. And the last approach is going totally general, that is saying, let's do video generation, and let's extract the actions using an inverse model from those generated videos as a proxy for the actions. Okay, so I'll talk about some representative work in each category of learning from human videos, and talk about what's their benefits and what's their drawbacks. So the first approach, explicit hand and object pose extraction. So this has been a very popular approach for a very long time, because that is what vision people think about robotics, right? Let's extract the states, and where the states meaning the hand pose or object pose, and let's train using those low-dimensional states. So I list some of the representative work, and I'll talk about one of those work, which is called motion trends, from my own group. So in this work, we're trying to use human VR data to enable motion level learning or motion level pre-training for robots. So yeah, so why we propose using human VR data. So because in the wild online human video is pretty dirty, in the sense of you can have various viewing directions, a lot of camera motions, and getting the ground truth of the hand is also very hard. So, but if you're collecting the data using a VR device, then the VR device usually come out with a hand pose estimation algorithm on their own, and it is also relatively accurate. So what we did is we take a Quest 3 VR device and ask our students to collect a bunch of first-person view VR video with it. And then what we want to do is we want to directly transfer those motions to the robots so that the robots can benefit from those human motions, and which is never seen in the robot teleoperation period. Okay, so our method is very simple. The main idea is we want to multitask human and robot co-training. So we have two parts of data. So the first part of data is the human data, where the human is wearing a VR device and trying to do a bunch of manipulation with his own hand. And then we also collect a bunch of robot data, where the robot data is naive teleoperation. But we force the robot data and human data to do very different tasks. So they don't share any of the tasks. But their motion might have some similarities. For example, some of the motion can be described by pick and place. And what we do is we use the VR extracted hand motion as a pre-training signal and shown on the top right. For example, the human is using his hand to close a laptop, while on the right-hand side, the robot data is doing totally different things. So then we simply mix those two types of data, and we want to see whether the human motions can be transferred to the robots in a zero-shot manner. So here, zero-shot meaning that the robot has never been teleoperated to do the same task. And actually, we find we could achieve around 20 to 30% of zero-shot success rates on unseen task, but seen task when seen task in the human data collection. For example, opening a box and put some toy into the box, or using the towel to wipe the surface of the table. But it's worth to know that those task success rates is only around 20 to 30% success rates. So this is because the human has an embodiment gap with the robots. But I think what is most exciting is not about the 20 or 30% success rate. It's about we could potentially use human data to train on a motion level to as a pre-training data for the robot policies. Okay. Yeah, so a little bit summary on this type of methods. The process that is super intuitive and straightforward and has pretty low sample complexity. Usually you can achieve generalization with a few thousand demonstrations on the human side. So it's not like you have to collect a huge amount of data to make it work. But the bad part is that it's very hard to get the ground truth. It's relatively easy to get a human hand pose, but it's very hard to get the object pose because object pose is defined per category. And as I said, if you want to define the object pose for a circular bottle, it's impossible to define a 6D pose because it's symmetric on one dimension. Okay, so then the second type of approach addressed this problem very well, called key points tracking or flow style intermediate representations. I'll talk about what are those intermediate representations in a short moment, but those are some representative work where I4 is way before those large models coming out. It's from and as well as two flow nets. So those two works are from University of Washington and SAMU's. There's some very good work that established those intermediate flow style representations. And ATM and general flow are two of my works that bring those large-scale vision pre-trained code tracker into those real-world videos. So I'll talk about what are those flow style intermediate representation are. Okay, so this is a work called general flow, which is also from my group. So this work is, as you can see, we sample a bunch of points in the scenario, and we track where those points move into the future. And we think those are very good intermediate representations because since we sample points, so it doesn't have any constraints on the object type we are manipulating. For example, we can manipulate a drawer without worrying about how to define the 6Z pose, because we can just sample a bunch of points on different parts of the drawer, and some of the points move and some of the other points doesn't move. So it can automatically deal with those articulated objects. And also we can have a pretty unified solution to the deformable objects and to human hand, and probably also to parallel grouper, all in the same framework by sampling points on the different parts of the scenario. And you can think of those points future movements as a type of 6Z pose in the original sense. But now each of the points is only tracking a single pixel in the video. Okay, so what we did is very simple. We first assume we have a embodiment agnostic data sets, for example, a human hand manipulate things data sets. And then we do the points tracking. So the points tracking is nowadays can be done very robustly thanks to the advance in computer vision using tools like code tracker. They can be tracked very stably, and the code tracker can also tell you when those points are being occluded and when it reappear again, and it can do the association pretty well. Okay, and with those track points, then we train a language conditioned future points movement prediction model, and then those models can be also transferred to the robots, or can be transferred to robots using a imitation learning fine-tuning second stage. Okay, and yeah, of course, there are some technical difficulties we have to overcome. For example, different point tracks has drastically different lengths. So you have to do the normalization correctly in order for it to be robust enough during the prediction time. Okay, so those point tracking based or flow style intermediate representation has the benefits of it can also include how the object is being manipulated. So and it's also very flexible on what type of objects you are manipulating, no matter it's articulated object or deformable object, you can all deal with them using the same framework. And only drawback of this approach, I think, is that it needs very subtle sampling of the points, because a lot of times what you are manipulating is a very small portion of the whole scenario, and your hands is also only occupying a small portion of the scene. So that makes the point sampling a little bit tricky, because you want to make sure that most of the points are on the moving parts, and you also don't include a lot of the static background pixels, which contain no information at all. Okay, so the third type of approach is called latent action models. So, and I also list a bunch of representative works. So what latent action models is doing is kind of saying, okay, I have a bunch of videos, but I don't have the ground truth action models, ground truth actions. So what we can do is we can train a action embedding that represents the action in a way that is similar to word embeddings. So we know that word embeddings are not explicit embeddings, not implicit physical quantities of what are each of the words, but it's a rather high-dimensional representation of those words. So latent action models is also similar. Okay, and there are several works doing similar ideas, and one of the earliest work is called playable video generation. It's actually video generation work, but they also discovered similar ideas. That is, we can probably recover a high-dimensional action embedding so that it can steer how the video is generated. So here I will talk about one of our group's previous work called forward inverse cycle consistency, which is trying to use a bunch of videos as the pre-training data without any action labels. Sure, I'll wrap up very quick. Okay, so the central idea is that you're given the first frame and the next frame, and then we train an inverse model trying to recover what is the action that leads to from the first frame to the second frame. And then this recovered action is input to a forward model to predict the next frame. And then we do a consistency loss between the next frame and the reconstructed next frame. And by doing this so-called forward inverse cycle consistency, we can recover the latent actions in the middle. Okay, and we also try to visualize what the latent action has learned, and we find that it has learned pretty meaningful semantics, such as moving left or moving right. And the more modern version is called LAPA, which is from Universal Washington, that they use the same idea, but on internet human videos and with RoboMdis. Okay, so the good thing about latent action models is that they are fully end-to-end, and they definitely include nothing about human priors at all. But the bad thing is that it could potentially learn image textures. The action embeddings might contain things that is irrelevant to how you move the robots. Okay, so the last part I'll very briefly talk about is using video generation with action inverse model. So what this method do, for example, the method of UniPy is saying, okay, I can generate the future videos. And if I can extract the actions from those videos, then those extracted action can act as a pretty good guess for what I need to do in order to complete this task. I'll skip through. And the good thing about this method is that this is most general, and you can potentially utilize all the video on the internet to do this. But bad thing is that it's very expensive to train, and but even worse, it's also very expensive to eval. Usually, generating a video costs a few minutes instead of a few milliseconds. And it's also very hard to generalize, and also the inverse model is also very hard to generalize. Okay, so with that, I want to conclude today's talk. So I talked about how to manipulate with priors. In particular, I talked about how to use VLMs to as actual information that we can extract during the policy training, and also about in the future we might want to use a lot of the internet videos to learn the motions in them and to enable the VLAs to generalize better. Okay, that's all for my talk, and thank you very much. If you have any questions, please come to the front.
So I think the tasks that you showed in the video to robot transfer were like probably still within the realm of tasks that probably something like a recap kind of key point based approach could feasibly address. Right? Like one of the downs you mentioned for the first set was that it's very limited expressivity.
Yeah.
But I kind of wonder like what's the envelope of tasks where we actually see where we still enable transfer from human data, but it is significantly more dexterous than what like a recap style approach could actually.
Yeah, so I think I think the honest answer is we haven't seen that too much yet, but we do see some small evidences that so with a method like recap, the motion is very mechanical, like it's moving, it's doing a bunch of basic motion planning and connecting them. But with those learning from human videos, you can achieve pretty smooth motions like this. But we are not able to achieve the the level of dexterity much beyond recap, which is mainly because human have 5-finger hands, and if we are using 5-finger hand robots, there are a lot of issues with the hardware, with the teleoperation. But I believe, and also I feel like in that case, the human data won't be able to zero-shot transfer to the robot because if you're doing dexterous manipulation, the contact will be very subtle, and you probably needs a lot more robo fine-tuning. But it could serve pre-training, so that's the hope. Yeah.
Thank the speaker again.
Thank you.
Presenting, and we will start with oral presentations. So the way this works would be that if you have slides, you can share them, and then this will be your camera and microphone.
Sounds good. All right. So yeah, so part of the workshop, the Generous Policies in the Wild workshop, is co-organized with the RoboArena challenge. And we think we did this because I think you know, a benchmarking challenge works, or fits the theme pretty well with how to develop and therefore how to evaluate generous policies. And so I want to talk a little bit about our effort into setting up this RoboArena benchmark, some of the things we've learned, and afterwards you'll hear from some of the competitors in this benchmark, and following that, some oral presentations. All right, so a brief intro for those who are not fully familiar. The core problem we were trying to tackle in this work was evaluating generous policies. So if a generous policy can, in the limits, do any task that a human might ask, to some degree, we have to actually evaluate these generous policies in a comparable degree of diversity with respect to scenes and tasks. And this poses a particularly hard challenge with respect to scaling in infrastructure and resources, because we actually have to take the robot to a variety of different places and actually evaluate it. So what we want is an approach that's scalable with respect to scenes and task diversity, but at the same time, unlike most evaluation approaches today, does not suffer from the reproducibility challenges. It's like today, for example, the way we typically evaluate policies is that we define some set of tasks to evaluate our policy and our baseline, let's say for the paper, and we evaluate all policies and all these tasks. But like 5 months from now, if somebody else comes up with a new VLA or a new approach, they can't actually replicate their evaluation setup exactly the same way I did mine. And there's also reproducibility issues with time, etc. So we want, so the core idea of basically our new approach is we enable scalability by crowdsourcing, and we eliminate these reproducibility challenges by removing standardization. So more concretely, our final recipe looks something like this. We had a global pool of evaluators, and critically, each evaluator, every time they would go out to actually run an eval, would not follow a prescribed sort of rule book of its set of tasks to pick from, but rather they would basically set up their own task, position the robot however they liked, set up whatever objects they wanted to, and ran an eval. And critically, each eval was A/B. So a pair of policies from the global policy pool would be given to the evaluator, and they would basically roll out both policies on the same task and pick their favorite. And together, at the end, we can sort of aggregate all of these pairwise evaluations into a final global policy ranking. So we released this, and we've had a decent amount of interest. So we actually have ran, I think at this point, around 7,000 evaluations. On the left are a small visualization dashboard that we've developed, where you can take a look at some of these things. And we've also ranked so far 9 policies. So I wanted to go over some of the lessons learned really briefly. One, the first lesson is, this idea does actually kind of work to a degree. So what we did is that, this is the final ranking sort of obtained by RoboArena. And to some degree, the ranking does match at least my intuition. So at the bottom, we have basically, well, at the very bottom, we have a binning approach, which does a very naive form of action tokenization that doesn't work too well. You basically need some sort of compression in your action tokenization to get policies that are not basically causally confused with respect to your action tokens. And then we have at the mid and the bottom some diffusion-based policies, and the top autoregressive policies that are particularly better at lineage following. And so it seems like more pre-training seems to help. So this just match your intuition, which is great. The other actually most interesting thing for me was that the demands of generalist policies, once you sort of give this problem or give the evaluation problem out to a large pool of crowdsourced workers, the demands that they ask policies to do is really, really diverse. So this is just one example. The task here is, I think, to press the spacebar on the keyboard. And I would encourage you guys to actually check out all the evaluations that we have logged on this website here. So I think this actually informs us developing policies. What are the type of things we need to train our policies to be able to do? And the final thing is we need to pay attention to safety. This is one eval we learned the hard way that we unfortunately let happen in the real world. Yeah, the robot basically just crashed itself. But yeah, I think the benchmark is still live, and I would encourage you guys to, if you are training policy Android, to submit it. Yeah, so I think now we'll have a presentation from our first and actually leading only competitor who was able to submit a policy that worked to the benchmark from Giuliano and Nicolette. So. Here a sec. It's not mirroring.
On this screen, can you do the share screen? Like, we need to share screen right now.
I just
Setting
up the sharing.
okay.
I think also on
So I think if you share it on Zoom, then it should be.
that's good. That's
If
good.
you just start. This is your camera and microphone for the stream, but I think it should just work. Like just stay around here and it will be fine.
Okay, the camera is this one?
It's this one, yeah.
Yeah, okay, cool. So, hey everyone, I'm Nikolai and my colleague Giuliano. Together we're going to present RoboMdis, which is a robotics foundation model via 3D understanding that we submitted to RoboArena. So just like a first quick recap of how roughly VLAs work today. We have two stages of training, and the first stage we are training a VLM where we inherit some common sense knowledge. This VLM is pre-trained on web scale data. And in the stage 2, we adapt this VLM to generate robot motion based on images and language. And in this work, we choose to address two of the problems that we have here. And the first problem is that embodied control naturally happens in a 3D world, but VLMs are limited to 2D images. And that means that the policy needs to learn this 3D world and this 3D knowledge from robot demonstration data. However, this robot demonstration data is expensive, and scaling it is difficult. So the main problem is that learning 3D via the robot demonstrations is very expensive, and we can probably do it better. So we choose to address that, but first, let's define what does learning 3D mean, really. For the purposes of this work, we define it as locating objects in 3D coordinates. And intuitively, why we do that is because most of the pick and place tasks that these VLA policies need to be able to do, they relate to being able to estimate positions of objects in 3D and the robot moving to these locations. So the insight here that we focus on is we can learn 3D with non-robotic data. And how does this non-robotic data look like? In our work, we choose to use just 2D images. So we don't need any robot demonstrations for that. And given these 2D images, we can ask the model, the VLM particularly, to warn tasks such as like output the 3D bounding box of a certain object or give me like the distance between two objects in 3D coordinates. So yeah, roughly how this VLM works, we call it Archimedes because of the geometry analogy. So it's a 3D aware VLM. In architecture-wise, it's based on polygemma as a base. So we just fine-tune polygemma. We make an architectural change where we add the Moji depth encoder to give us this new dimension, this third dimension of depth other than the 2D image. In terms of data, we train on just 200K ego for the images. So this is like significantly smaller compared to the robot demonstrations data that VLAs are trained on, or the VLM pre-training of polygemma. And we use like we compute these 3D bounding box annotations in order to get this training data. And they are basically computed based on a combination of Gemini plus SAM2 plus Moji. So like effectively, you just need like a point cloud, and from that you can compute the bounding boxes with segmentation masks. And this is very easy to train. It takes only 24 hours on 8 H200s. So using this VLM, we train a VLA. So the model looks like it has the same the exact same Pi0 architecture. The difference is that instead of polygemma, we start from this Archimedes VLM, which is 3D aware, and we still use a flow matching training objective. So for pre-training, we pre-train it for 300K steps on 24 OpenX datasets, which is roughly like 60 million frames. It takes 5 days on 32 H200s. And for post-training, so like the policy that we ended up evaluating on RoboArena, we just fine-tuned on Franca for a Franca robot based on Droid and RoboSet datasets. And now my colleague Giuliano is going to tell you more about the real-world experiments and results.
Yes, so, okay, sorry for the switch. I'm going to tell you a little bit more about how we approached evaluating this model, which we recently finished training, and our experience with the RoboArena benchmark, which is also the topic of this workshop. So after we got our model trained, we first ran some initial ablation study to determine if this 3D pre-training was actually helpful. And on some like in-house, let's say, tasks on the Droid platform, we saw that models trained on top of this VLM had better generalization and robustness. And so we moved on to more extensive testing of the traditional kind, where you like define a number of tasks and you evaluate all your models and baselines on it. And we focus primarily on, since we were targeting the Droid platform, on real-world experiments on the Droid platform. I write Droid-like because our cameras are slightly different, but it's pretty much the same platform. And we had two types of tasks, let's say. We had one more set of experiments where we ran very exhaustive evaluation on tabletop tasks in the same scenario, barring, let's say, the objects, the environments. And focusing here on reproducible conditions for all the models, controlled environment, high number of trials, and also trying to have tasks which were difficult for the models to do, but with still like a reasonable completion rate, say 50% for the better models. And then we also did some, before submitted to the benchmark, also some more vibe check experiments in some other environments around our office. And so the initial experiments, which were in environments like this, for example, they were quite promising. I'm not trying to dunk on any model here. I'm just going to like to show you how this, just as Pranav highlighted before, this kind of evaluations can be a little bit misleading on the actual performance of models. We had quite good results. 5.0.5 had just come out when we finished training our model. And we're pretty confident about the results on this kind of tabletop tasks, where we had like, even on a large number of trials, a pretty consistently high success rate. Then we moved on to these more like kind of qualitative evaluations, which I'm going to show some sample of here, which were pretty cool. Kind of like, if it plays, otherwise we will move on to the next slide, unfortunately. But Yeah, I don't think it's gonna work. Maybe we'll come back to that later, but okay. Okay. Okay, then we submitted our model on the RoboArena benchmark and we had all perfect episodes, right? No, unfortunately, that's not what happened. It's just like a very good example of cherry picking data. In practice, we had we're quite pleased with the performance of the model on the benchmark in some challenging scenarios, but there were a lot of failures and very unpredictable failure modes, which really helped to understand, what was missing in our model. If you look at the leaderboard, when I submitted the model, I finally named it DAM as like a do anything model, but clearly that's not the case. It's not that high in the ranking currently, but it's still doing not bad. I have to say, much better than we expected. So general thoughts on the benchmark, I think it's great because there is often a gap, as was hinted before, between the lab experiments that you can do and the actual real world performance of this model. So it's great that such a thing exists now to get a feeling for what your model can actually do. The tasks that are on the benchmark, I would say, if I had to make a comment on it, are currently quite challenging for what the VLAs, the state of the art, are able to do. Like I've been looking at the results on the benchmark pretty consistently since we submitted them before. And if you look, there is many situations of where the model, even the ones at the top of the leaderboard, are not able to do the task up to even 50%. So there's a lot of definitely work still to be done on this area, which is exciting. I would say I asked before the question at the CARS talk. For this, there is definitely a component of human bias in how the evaluations are defined, being preference-based. So clear and consistent scoring rubrics for the evaluators are something which is important to define for this kind of benchmark to remove this element of bias. And finally, it's a great to assess what your model can do, still not good to assess things like reliability of the model and robustness, for which I think this kind of more exhaustive evaluations are still needed. That's pretty much in the talk. If you have questions about the implementation details, feel free to ask. I have an extra slide. Yeah, thank you very much.
Okay. Thanks a lot.
Yeah.
Really, I want to say it's very impressive. You guys got to, you have learned quite a bit for this benchmark, that it's not super trivial to get a policy to up. And I think, yeah, we were very impressed with the performance of that model. Okay, we have maybe time for one question, if there are questions from the audience. Yeah, I think one thing that I was
sorry, I have a question.
I check evaluations.
Yes.
In your place, basically. Was there something different about those tasks? Do you feel like it was just less broad, or why did it do much better than times 0.5 there, for example, but then not?
So on the tabletop ones, yes, I think I said, on the tabletop ones where we had those results, honestly, we were quite surprised because we didn't try to optimize for it. Usually when you, for example, some models like OpenVLA are especially sensitive to how you position the camera. You're probably familiar with that. We didn't try to do any of this, what I call camera fine tuning. We just decided before starting evaluation, this is what we're going to do for all the models, whatever the results are. And then the results were quite good. But then after we submitted or after testing on other environments, we saw that Pi0Fast is still a very solid model. So I think in our case, it may have to do with different cameras and we have a different risk camera compared to Droid. We use the Intel RealSense, which has a different field of view. The way the external camera is positioned and the field of view as well is a little bit narrower, and we position it a little bit more behind the robot. So that's the best guess that we could come up with. Then
I guess as well, the tasks that we have evaluated on, usually the models can complete it 50% of the time at least. While on RoboArena, a lot of the tasks we saw that no model can actually achieve them.
Yeah, it's interesting. Maybe the depth-based model is actually more robust to the change in camera than the other models.
Yeah, I would very much like to make this change, but I feel at this time I'm not sure if we have this. We were discussing it today if camera viewpoint robustness is a feature that we can claim, but I don't think we have the data yet to say that. So I cannot make that statement, but hope so.
Oh, excellent. Thanks a lot.
Yeah, thank you very much.
Yeah. I think next we have Genie presenting over Zoom.
Yes, hello. Can everyone hear me?
Yeah, Genie, feel free to
Hello.
share your screen. I think he's presenting
Okay.
Maestro.
Yes. Let me just give me 1 second. Oh yeah, you need to allow me to share screen.
Okay.
Okay. All right. Can everyone see my screen and hear me?
Can you say something? I think it's more about a mic. Can you?
Oh, hello.
Is there a way to get this mic, this audio output onto the room speakers? Like I am already connected to this, but do you know if there's a way to get it to actually project to the here?
Is this any issue from my side or?
No, I think we need to figure out
Okay.
how to get audio onto our room system.
Got it.
Can you try talking again?
Yes. Hello. Can people hear me?
Probably not any better, right? One thing we can try is to put this thing close to this speaker. Should we try that?
Sure.
1 second. This is a very hacky solution. Could you try saying something again?
Yeah. Hello.
Can you
Can
guys
everyone hear me?
okay. Okay, I think this should work. Very hacky.
Yeah. Thank you, Carl. Hi, everyone. My name is Junyao Shi. I'm a PhD student at UPenn Graz Robotics Lab. And today I'm presenting our new work. It's called Maestro, Orchestrating Robotics Modules with Vision Language Models for Zero-Shot Generous Robots. So I want to first motivate the method by talking about what are the prevailing paradigms of robotics today. And things were at CoRL. So the first one I'm going to talk about is, end-to-end models trained on massive robotic-specific data sets. And we have seen so much success here, right? Like including things like, sorry, I don't know why there's audio, but including things like Pi0 and Gemini Robotics. And the pros are pretty clear. These are very scalable recipe and general purpose. But I think, as Ken Goldberg might have said in some other workshop, should we just wait around first such that we get enough coverage on everything? And as we understand it, these models are quite data hungry. Like it's very expensive to actually get coverage on probably every single task, every single scenario that we care about, even though they have made amazing progress. The other paradigm, which might be something that's kind of in the past, but I think it still works very well today in many scenarios, is what we call like good old-fashioned engineering of modular systems. Right? So these are like, okay, so in these videos, we see things like MD Robotics on the left, that's doing like packaging take place in the factory that's deployed. And like in the middle, there's the Flingbot. And here we see something that's like Waymo. These models are like very reliable, high performance. They're designed for that task, very well tuned and engineered. There's a lot of rigorous work that's done for them, and they're very high performance. But the con is that they're not super scalable, right? This system only works in this setting, and to make that work for even one setting requires substantial task-specific manual effort. So is there a way to actually get the best of both worlds? So what are the best of both worlds, right? As I explained, in the end-to-end scenario, that's the generalization across many different settings. And for the good old-fashioned engineering approach is probably the way to tune and orchestrate different modular components for good performance on this one task. And if we take a step back and consider like an alternative approach, which is vision language models, right? What they're good at is things like common sense reasoning. And we have seen a lot of like LLM and VLM agents. They're able to use different tools and APIs and compose them and orchestrate them for the downstream different kind of purposes. And they're also very good at coding. If something is presented as tools with good documentation, they're able to reason about it and use them and like basically iterate them. Like anyone who has used something like Cursor will know what I'm talking about, for example. And the weaknesses of these VRMs is that they don't really have the robotics knowledge, right? They don't have access to, they cannot do collision avoidance by itself just by outputting text. So can we somehow use them for like good old-fashioned engineering with a little help, such as the old ways that's a lot of manual efforts on one task can potentially be more scalable. And this is what we want to present as a new method, where Maestro is basically like a VRM as an agent, but more like a robotics agent where it has vast access to various different tools. And we show that through our paradigm, it can actually zero shots with no robot data be deployed like various different tasks with a very good performance. So our key insights are, first, VLMs can use tools, right? So and by using tools, I meant like more like understanding APIs, understanding how to write code and so on. And so let's just give them a lot of quality robotics related tools, right? And then the good thing is that robotics tool modules, such as collision planning, such as perception, and so on, and a lot of things for reasoning are all expressed in code. Even a VLA, like even using a Pi 0.5, is actually expressing code with examples and documentation and all of that, right? And then the other things is that VLMs are very good at reasoning. So let it reason in closed loop. So we can first make the VLMs plan a little bit, and then it can react by looking at what it has done and all the outputs and the code programs it has written, and then decide, do we need to like do something else or keep going, right? So you can plan, react, and replan. So what are the benefits of such a system? So first of all, like there's like if you provided the right amount of like robotics modules, right? Just as in the old way of like old-fashioned engineering, you might not need that much robot data. Sometimes you don't need any robot data, right? Because if you just orchestrate them correctly, sometimes that's enough. And this is a potential recipe, perhaps, for automatic data collection, even for for training VLAs. And it also inherits all the other like good things from the modular system, such as interpretability, debuggability, and extensibility. And specifically, we'll show with some preliminary experiments that you can even improve by evolution by doing like localized spot edits to the tool repertoire or the policy code. So and then through this recipe, we don't really need to retrain, refine tune with like a lot of large scale data collection. And the final thing is that to me, it's just like everything is a tool module, even VLAs, and we also show some preliminary experiments showing that the system can like efficiently use VLAs for to perform tasks that VLAs themselves cannot even do. Right. So on a high level, the method is very simple. So as I explained, right, we just give it a lot of tools, and I'll share some insights on what are the tools and what are the guiding principles for us to select the tools. So it sees all the tools, and given the prompt given the task instruction and like the current image of the environment, you will start reasoning, planning what code to write. It writes the code, execute it, and the execution results will go back as images and like code output, right? So and then basically this interface is very simple and closed loop replanning, but the point is that we need to give it enough modules and tools such that you can translate something high level, such as code and reasoning, into low level robotics actions. So yeah, I'm not going to go into too much detail about like the laundry list of many tools. I think we did make an effort to see like what are the tools that are being used in previous systems, such as code as policy, embodied chain of thoughts, or even the agents presenting the Gemini robotics papers. And we see that a lot of times where it wasn't able to do very well, it's because it actually was able to reason, but then it struggles to turn those reasoning into actions. And it's because in those cases, it doesn't have access to the right kind of tools and modules to enable this translation, right? So by actually adding a lot of critical things, which I'll talk about with some high-level insights later, then like we actually can massively improve these performances and get it to like at a VLA level or even surpass VLA in many different situations. So what are the principles for us to build this Maestro toolsets? So very quickly, things like we need to have different level of hierarchy for perception modules. It might not enough just to have something like bounding box or segmentation. Something more precise, such as key point selection and pointing might also be necessary. And also we found that active perception is very important, especially because it actually like having this module will actually help our system to improve the performance of other modules where, for example, the depth perception or grasping might help from like getting different image views and having a better reconstruction as an example. Or you might find some like angle to interact with the object that's not immediately like obvious. And we also find the geometry and linear algebra kind of tools very important for scaffold spatial reasoning, just by giving it some help in terms of how to build vectors, how to translate rotations into translate rotation matrices into orientation and so on, right? And then compute like distance and so on. It actually helps a lot for them to think step by step and improve the spatial reasoning of our system. And also, in order to use a VLA which runs very fast, real time, like very fast, we actually have to have a very fast monitor to interrupt it, such that when the VLA has finished a task, we need to tell it to stop. So we need to have kind of like one of the tools we have is a very fast inference local VLM as a monitor. And collision avoidance is, of course, very key for object interactions. And a lot of previous system doesn't really have this. And in our experience, it fails at various different tasks. And we also show some mobile results. And there we see that the semantic map as a tool is very important for efficient long horizon planning. So first, I'll show some like tabletop results. So our baseline, are we out of time?
Short on time, if you can wrap up like 30 seconds or so, that'd be great. Thanks.
Oh, okay. Yeah. Let me just wrap up by saying that we have I failed to show a lot of videos due to time limits, but we have basically our we really outperform like our baselines such as like Pi 0.5 and the Gemini robotics agent in many different tasks that we run. We didn't thought it was possible for the kind of agent system to perform, and it's really like embodiment, not embodiment specific. The same system could be deployed on any tabletop or like mobile robots as long as has access to the right selection of tool repertoires. And as I mentioned before, you can essentially improve from evolution just by like after a trial, you can look at what is the generated code, what is the analysis, what is the output, and use that as an in-context example. So you can like fully open this door, and you can also use like a VLA as a tool where like even though it has like even superior performance than like without VLA as a tool, but it's like much faster. And even though VLA by itself is also pretty fast, it doesn't actually like, for example, this kind of task where it requires a lot of common sense reasoning, it's not really able to do something like that. And obviously, there's a lot of limitations to this, like such as speed is one thing where it needs to like spend time to plan and replan, and you're also limited by like the tool mistakes. But like even from this week, right, we see like so many new things come out, like the Gemini robotics ER or Q3 VL. So these tools and VLMs agents continue to improve. So that's what makes me believe that this is potentially a scalable method. And as a conclusion, I think this is, it's a very cool method where we leverage different tools for zero-shot general manipulation, and we can even scale up like the good old-fashioned engineering without manual efforts. And one promising direction, I think, and this is something that's probably ongoing for us, is how do we use this to generate reasoning and even action data for UIs, such that maybe this kind of reasoning doesn't need to take so long, and we can improve the speed and efficiency of such a system. And thank you.
All right. Thank you, Genie.
Yeah. Cool. I guess there's probably no time for questions, but yeah, thanks.
Yeah, probably no time for questions, but I will say, actually, reading
Mm.
the workshop paper, I was quite impressed by how good the model actually was. I think it says something about good old-fashioned engineering and some of the things that type of approach might enable.
For sure. Yeah, thank you.
I think, for our next talk, we have Matteo, who'll be talking about his approach or his paper called VAMOS.
So the best is for you to share slides through Zoom. Are you on the Zoom already?
No.
Oh, did you get a link?
Ooh, I don't know if I did. Let's do it. An email link? Oh.
Yeah.
Oh, there it is. Oops.
Yeah, if you just join this. Just without audio or video, like it will just all be on my laptop. You will just share your screen there.
Thank you. Also. Good. Yeah. Okay. Hello, everyone. My name is Matteo, and today I'm going to be presenting VAMOS, a hierarchical VLA for capable and capability modulated and serial navigation. This is a work out of the University of Washington with all my people. So I'm going to talk about a tale of two somewhat at odds objectives. So one of them is that we want robotic policies that generalize to a diverse set of environments and embodiments. However, we also want them to align with robot-specific capabilities and constraints. So for example, here in the top row, you have both legged and wheel robots from River and Unitree, which are able to do a lot of things, like go upstairs, go in water, go up any ramp. And in the bottom, you have wheel robots, which do not have the same capabilities. But even within wheel robots, you can have big robots, which this bottom left one is called Crusher. It can crush through anything. And then smaller robots, which are fast, but also quite capable. The thing is that they do have specific capabilities and constraints, and we want to be mindful of that. So in the last couple of years, robot policies have been training with increasingly larger data sets. So this is a slide from Kevin Black last CoRL. And you can kind of see like the data used for training GPT-2 is a much larger dimension than the ones used for robotics at that time. And there's this recent paper on the VLA, which also trains on navigation policies with a lot of data. It's 9,500 hours of data. And this has been the trend with navigation as well. So before this paper, Nomad was trained with 100 hours. Now it's like 100x that, which is very impressive. But for context, we're going to show something that works with 30 hours, which is much smaller, and it has pretty good performance. So what happens when you pull together data from robots with different capabilities? One toy example that I like to use is, let's say you have a robot that needs to go up these like stairs or ramps. If you have a legged robot, then it can do it no problem either way. However, if you have a wheel robot, there's only one way it can do it, right? The issue when you pull together data with different robot capabilities is that performance degrades, and this is navigation performance. And the reason why it degrades is because the model needs to do two different things. It needs to learn high-level navigation semantics that generalize across a wide variety of environments, scenes, etc. And it also needs to infer the low-level embodiments capabilities. And so you're burdening the model with two different tasks, which are quite challenging. So we address this via hierarchy. What this lets us do is maintain the generalizability and steerability of VLMs while being cross-embodiment by design. And if you're ready to see how, vamos. So I'm going to show you kind of the system overview. Our system is quite simple. You first take an image of what the robot sees, and then you encode the goal location as a coordinate pair of tokens. Then you pass it through a VLM planner, and then you get
a bunch of 2D trajectory proposals. So our interface between the high and low levels are just 2D points and paths. Then you take this through what we call an affordance modulator, which is purely trained in SIM. These are very small, very cheap to train NLPs. And now you get effectively a filter, which takes these proposals and aligns them with the capabilities that the downstream robot can actually do. So the VLM planner is trained with diverse heterogeneous real-world data from 4 different data sets, 3 different embodiments. And these span a bunch of it's okay. A bunch of different scenes like outdoor, off-road, indoor, urban environments. And then we train these per embodiment affordance models safely in simulation. These are pretty cheap to train because we have simulation. We only use height information, so geometric data. And what you get out of it is something that starts to resemble a cost map, where for example, here, this yellow area is whatever the robot knows it can do. And purple is what it can't. So for spot, both paths are fine if you want to go up some ramps or stairs, but for this small hound robot, it can't. So one of our key results is that Vamos outperforms both model-based navigation stacks and navigation foundation models in challenging real-world courses. And these are in a wide variety of settings. They're fairly non-trivial. There's a lot of tight corners, different lighting conditions. There's stairs, there's rough terrain, there's a bunch of different conditions that make it hard. You don't have to look at the whole table. The key takeaway is that our model outperforms both your classical modular stacks, which are usually well-tuned for a specific embodiment, and these type of foundation models for navigation, such as Nomad and Naviva, and we get great navigation performance. So actually, I want to show you what one of these experiments looks like. This is in our forest outdoor experiment, and down here you're going to see the VLM predictions. This red cross is where the robot needs to go, so that's kind of like the waypoint. This is running 3x, but it runs real time. We have a 3-minute timeout on the whole course, and it's a little choppy, but you can kind of see even though at points it may sniff a little bit around the bushes, it gets to the goal, and that's pretty impressive, I think. I'm going to show you also what other methods do, just kind of to give context. Modular stacks usually use geometric cost maps and then use an A-star type planner. What happens here is that at the interface, they fit. So here, for example, these overhangs appear as not traversable, but they are. It's just that, because of the way you encode modular information, the planner just freaks out. You end up with something that fails. Nomad appears to, out of distribution, struggle a bit with actually finding goals. And so we ended up just intervening whenever it got into unsafe locations, and then it seems to be great at exploring, but unfortunately it times out, and it never makes it to the goal in the more challenging courses. Then we actually found that, well, let's finish running. Yeah, it times out. We also tested against VI Planner, which is a pretty capable perception and planning system from the ATH people. And actually works great. We found that where it doesn't work great is when it needs to do long-range planning across a long horizon. And our model does a bit better. And finally, another one of these foundation models, Naviva, has a similar challenge as with Nomad and ends up going straight. It's a big model, so it takes a lot of time to run, ends up just timing out. Okay, so another key result is that Vamos enables cross-embodied navigation by design. So with the same high-level VLM planner, we're just swapping out the low-level NLPs. And here we have the exact same scenario I motivated with, where we have a robot that tries to go up some stairs and ramps. With Spot, it gets there every single time. It just chooses more 80% stairs, 20% ramps, but we achieve 100% success rate. And the cool part is that with this small wheel robot, we see that we also get pretty high success rate of 90%. It takes the ramp every time because it can see that downstream there's these stairs that it cannot do. And that affects the long horizon planning, which makes it get to the goal 90% of the time. We compare against the most successful baseline, VI Planner, which was trained for animal-legged robots, and so it's pretty good with Spot, a similar size robot. However, we see that, so yeah, 100% success rate. We see that for this hound robot, it tries to do the same thing, and obviously that doesn't work. And so we see that it does not get to the goal a single time. Ours, just by swapping these cheap to train modules, you can get cross-embodied navigation by design. And lastly, we show that Vamos is easily steerable through natural language. And so I didn't talk much about this. Come talk to me if you want more details or go look at our website. But we annotate a bunch of these navigation trajectories with GPT-5 like annotations of what happened in those paths. And what we see is that if we click on a goal here, say no preference, it still gets there. But if we add preferences, for example, make a sharp right arc to avoid the people, it does it. If we ask it to go left, it does it. Same scenario with ramps and stairs. If we ask it to stay left to take the ramp, it takes left. And if we ask it to stay right, it takes right. Another one here where without a preference, it kind of goes all the way down the path and then to the right. But if we ask it to cut across the grass, it does it. And finally, the same scenario, but with going in between bike blocks as well. So the key takeaway is that Vamos lets us maintain generalizability and steerability of VLMs while achieving effective cross-embodiment and, importantly, maintaining robust performance in navigation tasks. So with that, I want to thank you for your attention. Thank you to the team. And here's our website. We will be releasing this soon on Archive and Twitter and all. So yeah, looking forward to hearing from you.
You guys have one question?
Is there something we can learn from this setup of like real data pre-training and then sim data filtering essentially for manipulation? Like you did navigation, of course.
Right.
Is there something we can learn?
I think for manipulation, there's still the same challenge or idea where like different embodiments have different capabilities. So one of the differences, for example, one arm manipulation versus bimanual manipulation enables you to do different things. Or if you have more dexterous grippers versus not, you can do different things as well. So I'm not sure how the idea of like in navigation, it's quite easy to operationalize this as cost maps. Maybe there's like a different way of learning like value functions that let you know if you want to achieve this with this embodiment, you can versus you can't. So originally we wanted to do this with more like an RL type value function. We found that just supervised learning works better. But I think the idea applies as well.
All right, let's get to the table.
Thank you.
I think the next presenter is UA.
You're on Zoom, right?
Yeah.
So yeah, I think if you don't need to do any of this, you just need to share your slides on Zoom and then I will present them.
Okay. 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 Hello, everyone. I'm Guanghui from AJ Bar Research. Thank you for the organizer to give us the opportunity to present our work. Today, I'll introduce Genie Invention, a unified world foundation platform for robotic manipulation. Here's a quick outline of today's talk. Firstly, I'll talk about our motivation. As we all know, building scalable robot models is hard because there are many challenges in getting real-world data, in generalization, in evaluation. To address those challenges, many embodied world model approaches have been proposed, such as for data augmentation, DreamGen, for unified representations like LAPA, for closed loop simulation like 1X world model.
existing approaches handle augmentation, representation, and simulation one by one. They can't work well together. So we need a single unified world model that can generate data, learn representations, and evaluate policies all in one system. I will give an overview of our project. Here's a short video. When the box is closed, the model should remember yellow candy requires a blue stamp, white candy requires a red stamp. It can retry. Sorry. They are all generated by our model, GE model. It can go across many environments. Okay. Let's dive into the details. First is our GE-based water foundation model. For its architecture, it's an extraction conditional video diffusion with DIT-based model like RTX or Cosmos. It uses hierarchical latent space, fill-in fields, actions, and tests. It uses temporal memory for long sequence consistency. For its training recipe, it's trained on AGI board world beta 1 million video sequence. In the domain adaptation phase, it transfers general video generation capabilities into the robotic manipulation domain. Finally, it learns model with temporal resolution required for downstream action policy training. Second is our Genie GE Act water action model. For its architecture, it predicts action from latent video representations produced by GE base. It uses a flow matching decoder for continuous action trajectory generation. It also uses cross-frame attention to capture dependence between past frames, current state, and instruction context. For its training recipe, action pre-training optimized the action decoder to predict action from latent video representations. Video adaptation fine-tunes the video generation module with task-specific data for better generalization. Action adaptation fine-tunes the action head and the video generation module with control signal for accurate action. Finally, it's our GE sim word simulator. For its architecture, it's an action conditioned neural simulator that predicts the future video frame given robot action and the current state. It uses cross-frame attention and temporal memory to maintain physical and temporal consistency. For its training recipe, it's initialized from the high temporal resolution pre-trained model GE base. We also use AGI about word beta and augment the data with failure cases from teleoperation and real robots to improve performance. I will show our results. First, as shown the table below, GE-based outperforms open source models like Cosmos, OpenSora on key metrics like motion and scene consistency. For GE Act word action model, as shown the right video and below the table, GE Act outperforms Groot N1, Pi0, and UniVLA across many tasks and embodiments, showing its strong advantage. Finally, it's GE sim as shown the right video and finger. GE sim generates multi-view videos and can support closed loop evaluation on real robot. The first line is running in real world. The second line is running in our world simulator. The third line is the action predicted by policy. The lighter for open, the darker for closed. Finally, I'll give some take-home messages. Genie invention is a unified word model platform. It combines word modeling, policy learning, and action condition simulation into one system. Based on that, GE Act is a word action model. It delivers high performance on unseen robots and normal tasks, showing strong cross-embodiment transfer. Finally, it's GE Sim, a word simulator. It serves as an action conditioned video simulator, enabling closed loop evaluation. Most important, it's all open source. Thank you. Thank you.
Okay, I think we have time for one question. Actually, I have a question. So I wonder if you have observed any correlations between the types of tasks that are most difficult for the VLA and for the model. Like are certain tasks that are really hard for the VLA also hard for the model to produce accurate renditions of? Yeah, I was curious if there's correlations between
maybe my colleague can answer this question.
tasks that are difficult for the action model, the VLA, as well as the video generation model.
Okay. I mean, one same task is typical for both models. Well, typically those models are those tasks are typical for the action models are context rich, especially on long horizons, things like that. But those things are not so difficult for world model. But especially if there are obstacles or if you can spatial continuity if object is being hidden and then show again. For those tasks, the world model is maybe not so good. But for the VLA, it's because it's more Markovian. So it's response instantaneously as the object shows up. So at that moment, the VLA just works okay. Of what one model is now.
Okay, thank you.
Well,
Yeah.
All right, and that concludes orals. I think next is poster session and coffee break. I think the posters are right outside in the main hall. And then we'll be back here at 3:30 for Laura's talk. Thank you.
Me?
need audio here too. And then this one is muted, right?
Yeah.
Okay.
I think I've before, yeah.
Cool. Pranav, we're starting. Excellent. Then we're back for the next talk of the day. It's my great pleasure to introduce Laura. Laura used to be a PhD student at Berkeley, now works at Pi, and is probably one of the people at Pi who spends the most time with the robots and knows all the ins and outs of deploying robots into the wild. So really excited to hear from her about that experience.
Thank you, Carl. Yeah, as Carl said, I'm a researcher at Pi, and I'm really excited to be here today to talk about my experience deploying a VLA in real homes. I'll be talking in particular about my experience back in April when we took our robots to Airbnbs around San Francisco and tried to get them to clean totally unseen bedrooms and kitchens, zero shot. We are motivated by this longstanding goal of many of us in the robot learning community, which is to send robots out of the lab and into real life environments and have them do useful things. Why is this such a challenging problem? Our world is so diverse and unpredictable. I don't know what kinds of drawers, nightstands, pillows, cabinets are going to be in a new home, or things like the distribution of kitchen layouts in San Francisco, which is also certainly different from those things in, say, Korea. And we want to be able to handle it all seamlessly, just as we would be able to do as humans. Now, although it might look simple, what we're asking the robot to do is actually really complex. We're dropping it in a completely new environment and asking it to clean the room. The robot's having to situate itself in these new places, each with unique furniture, objects, layouts. It needs to recognize based on context and do some reasoning about what needs to be done to accomplish the broad task of cleaning the room. Then it also needs to adapt its low-level behavior to the particular demands of its environment. How do we get robots with human-like intuition and understanding of the world and its embodiment to be able to navigate totally new spaces, adapt, and compose its learned skills to those situations? We have reason to believe that the solution could take the shape of training on internet-scale data, since LLMs and VLMs have remarkable reasoning and generalization capabilities. So what we did is train a large vision language action model that inherits the broad understanding and reasoning capabilities of internet-scale VLMs and connects it to low-level robot control. Now, the question that remains is what kind of data should we train this VLA with to elicit all the behaviors we want? Deciding on this composition of this data is challenging because there are just a lot of unknowns, right? We need to actively design physical data collection in the real world when we're training these VLAs. So what I'll do is go through all the data types of data we ended up training on and some considerations about each, and then we'll look at some analyze some experimental results. So we train on teleop demonstrations from the mobile manipulation platforms we ultimately test on, since this is the most straightforward thing. But this is relatively expensive to collect. How much of this data do we actually need if we have a foundation model to start with? And how diverse does it need to be in order to generalize in the way that we want it to? We also designed these more lightweight static robot arms that clip onto furniture. These aren't the same as the target robot platform, but they're more portable, and it would be really convenient if, because it's easier and cheaper to collect data with, but we don't know yet if we can actually learn anything useful from them. Now, if we want to effectively generalize in open world settings, where we really need the model to understand its surroundings and to really reason about what it needs to do in out-of-distribution scenarios, how do we make sure that the base internet scale model that we're adapting actually retains its reasoning capabilities? Lastly, we've accumulated tons of data collected in the lab across several different embodiments. Can this help with open world generalization outside lab settings? That's the main question there. So to shed light on these, we tested on some basic tasks in some mock environments we built. In this first experiment, we're looking at how the variety in environments we collected the mobile teleop data in affects zero-shot generalization to a new environment. To understand what is the upper bound on the zero-shot performance we could expect, we collected data in the test environments and trained a specialist model per test environment. Then this is the the performance here in the dark green bar. Now we fine-tuned the same pre-trained model that we fine-tuned in domain data to get this green bar on the same volume of data, but collected only in 3 randomly selected training environments, and see that with just 3 environments, the model struggles to generalize. But if we train a model with data from about 20 different homes, we see a pretty big improvement in zero-shot generalization. Finally, at about 100 locations, zero-shot generalization is actually just as performant as the in-domain specialist, which was pretty surprising to me. Now, it's important to note in both of these cases, the model has been pre-trained on the broad cross-embodiment diverse task robot data. But with these observations, this gives us a sense for a path towards our goal for zero-shot generalization. With a strong foundation model, we certainly need diverse data to generalize, but it doesn't take an infeasible number of training environments for performance that competes with what the same model is capable of when training on data directly from the test environment. So as I said, these numbers from a model fine-tuned on, we can see that without pre-training, so these new bars are showing kind of analogous to, or the same data mixture, but without pre-training. And we can see that without pre-training, all performance suffers. For in-domain data, the performance is halved, but more importantly, we see that it's basically completely make or break for zero-shot generalization to a new environment. So pre-training on diverse data seemingly is a critical enabler for learning anything from the diverse location data and doing so pretty efficiently. Like I said, only from 100 locations. To give a simple visual example of what failures could look like when you have a lot of data volume, but not enough data diversity in environments, here's the robot attempting to open this drawer in our office, and it has like a horizontal bar handle. We see, and there's no data collected in this environment. And we see that the robot's clearly like trying to go for the handle, and it's like, you can kind of get a sense that it understands what it's trying to do, and is making a decent attempt, but it's approaching the handle in a way that's just not ultimately going to be successful. This was just kind of funny to me because I guess what this read to me was like, it thinks that it's grabbing a knob. It's trying to grab a knob. And so like, I think that makes sense. Like if we didn't collect enough data for the robot to understand that this is like how you interact with drawers with knobs or different types of handles, it's gonna make mistakes like this. But after seeing enough drawers of varied types, like here on the right, these is like actual data that we collected from, even though it hasn't seen exactly the same like metal horizontal bar drawer, it's able to grasp the concept of this horizontal bar handle and do the task. So we know that both diversity in training environments, we collect the mobile data in, and broad pre-training are really important. Next, we'll try to understand a bit more about what matters in the pre-training data distribution. So to do that, here we're going to ablate each component of the pre-training data sources that I mentioned. So starting from our full recipe, which includes mobile teleop data, the other robot data as I described, and web data. If we compare this full recipe to removing the other sources of robot data, performance is basically almost slashed in half. So this is like the very far right bar when we remove all the other robot data sources. So while these aren't immediately task relevant, we believe training on this data indeed provides a better foundation from which to learn quickly and provides stronger generalization capabilities. Now, we see that in this case, in these experiments, the web data doesn't seem to matter too much. So that's the gap, the first 2 bars. But these plots, to me, really don't tell the full story. So in that last experiment, we were looking at whether a particular task was ultimately completed, but we can also evaluate the ability of the model to correctly follow language commands as a separate evaluation axis. And where we found web data to be a big unlock was in accomplishing super long horizon tasks, especially when we took the robot to unseen environments in the real world. Because we found it to be to really improve language following, especially in out of distribution scenarios. So I wanted to share this. Okay, yeah, really neat example where Michael was testing. So we went to this like new Airbnb. We were trying to test like, okay, what can the robot do? And like, what is the upper bound of what the mobile, the model is physically capable of doing in this new kitchen? And we do that by just asking it to do different things and setting up the scene for it and then just seeing what it does. And he was testing it out, giving the robot commands. And I was just really surprised at just how well the robot was listening to him and executing on what he asked, despite in many cases there being a few things the robot could do. So like in the beginning, like the robot was over here, it could have closed the microwave, or it could have like put the plate in the drawer, or maybe it could have put the plate in the sink. Here we can clearly see at different levels of granularity that the robot is really responding to the particular prompt that Michael's giving. And this kitchen was especially kind of unique in that it has like easy access to this dining table. And the robot was easily guided to bus the table in addition to the other tasks that were more in distribution for kitchen cleaning. So this wasn't just for testing the upper bound on the robot's performance with a perfect high level direction. This became another convenient way to collect data. In the paper, we've referred to this as verbal instruction data. And generally what we've seen is that this can really help get the robot to understand how to wield the skills it has latent into doing more impressive, longer horizon tasks, and even to do things that it was never explicitly demonstrated to do. And just to be clear, we didn't train on the data from that environment when we showed our zero-shot results, since then it wouldn't really be zero-shot. It was just for illustrative purposes. Okay, so generally we saw this better language following in Pi 05 than with our earlier iteration Pi 0. While some of that might be attributed to the nature of the diverse data that we collected, I want to make a quick aside about some important tweaks to the training recipe. So the Pi 0 model glues an action expert onto the VLM during the pre-training phase, and training that with robot data is the primary objective of the pre-training phase. And post-training is largely to push the model towards higher quality behaviors. In contrast, Pi 05 pre-training involves co-training with web data on VQA and bounding box detection and action prediction, all using next token prediction, and then adds an action expert during the fine-tuning phase, and we find empirically this leads to better transfer. This is important because it really unlocked the ability to teach the robot to do more impressive tasks in these new environments through language. For more on this topic and how to do this better, see Danny's paper. Okay, so now the importance of this verbal instruction stuff was really made obvious when we took the robot to real homes, because this is how we kind of realized that it's really powerful if you can have a generalist model that has all these low-level capabilities, you can compose them to do more impressive things. And this brings me to the importance of real-world evaluation. And I want to talk a bit more about some things that surprised me when evaluating or playing with the models and other ways that this has shifted my perspective. So at some point, I was trying to see if the robot could do this non-pick-and-place task of neatly folding and hanging a towel on an oven handle. To give it what I thought was its best shot at working, because I thought this was a really hard task, I collected a bunch of data in this specific environment and fine-tuned a model specifically on this data and some other task-relevant data, but it's all of this task. And so what you just watched is an eval I did where I tried to make it as easy as possible, starting the towel flat on the stovetop. And even then the model was like struggling a lot. And this was kind of sad for me because I was like, well, maybe this task is just not observable enough and maybe it's too hard. Coincidentally, on the same day, I went over to one of these other mock homes and I was testing the general model that we've trained on all the mobile data and on one of the like simpler evaluation, like standard task evaluation suite that we had. So like one of those tasks is putting the items that are on the countertop into a drawer. So I gave it the prompt of like, put the items in the drawer. Now, so I'm like sitting there watching the robot go. And the robot's doing something reasonable. Yeah, it's like opening the drawer. Oh, like it's straying from the drawer. And then it decides to just go off on its own. And I'm getting confused. I was like, what is going on over there? And then the robot proceeds to grab a towel that I like couldn't even see like in the first place and hang it almost as to prove to me that it like I can't actually do this task. And to reiterate, like we didn't collect any data from this environment. And clearly I was like shocked because I didn't even see the towel in this environment. Okay, maybe we can skip to the end where it actually hung it. So yeah, I think this was just kind of like an aha moment for me. Like, why am I showing this? Like, it seems like a failure because the robot actually ignored me in this case because I was asking it to put stuff in the drawer. But in my mind, this was very meaningful because the robot did something totally unexpected. And so what I took away from this experience is first, rich evaluation environments are opportunities for expressive policies to really shine and for you to discover capabilities it has that you might not have expected or even intended. Second, this really solidified in my mind that training on diverse tasks and environments can really outperform specialists. And then if you have the capacity, usually more diverse data is just better. Another way I've really enjoyed interacting with these models is poking it and seeing how it reacts to the world changing in adversarial ways, because its behavior tells us a lot about what the model has really learned and how robust it is. So here I'm moving the basket around and continuously throwing clothes for it to pick up and getting into weird situations where the basket or clothes are not directly in the robot's line of sight and the robot needs to go search for the laundry basket. Clearly it has internalized this concept of this is what a laundry hamper is. And my goal is to make sure that the floor is clear of dirty laundry and that those clothes end up in that basket. Here's another example of testing what the robot has really learned. So the robot was asked to clean the spill. It successfully goes ahead and does that. But then Chelsea continues seasoning the table with some condiments. And it's fun to see that the robot really reacts to those interventions and quickly goes to clean up the new messes. It's not just kind of like indiscriminately wiping at the table. Lastly, I'll give some parting thoughts from reflecting on these experiences. So first, some things that I used to think were going to be huge hurdles turned out to be actually quite tractable in practice. For example, having a robot run autonomously and continuously doing its own thing without any physical intervention for tens of minutes at a time, we found this to work much better than I expected. The robot is really able to operate autonomously for long periods of time without help. And second, the main concern of this project in the first place was environment generalization and all the challenges I described at the start of this talk around that. And I think we found that with these different data sources, enough of that data and a training recipe that soaks it all up, this is also pretty achievable. At the same time, some problems we thought were hard remain hard. I think what we demonstrated was pretty remarkable and was the result of a huge effort from a team of researchers, engineers, operators. But we're still not at the point where we can just ship a robot to, say, my actual house and have it do all my chores. So what's missing? A big one is reliability. I'm impressed by the failure recovery of our models, but we have to be at the point where it's not causing any failures that could potentially harm itself, its environment, or the people around it, on top of recovering from any failures super reliably. Another one is speed. While this isn't really a blocker, the speed at which the robot performs these tasks is pretty far from human-like speed, and therefore is not maybe the most practical thing. And while we see this improves with more data, it's still not really human level. On top of that, there are just some things that the current hardware we're using is just not enough to fully cover. For example, if we want the robot to not only put the dirty dishes into the sink, but also wash them, the robot needs to be water resistant. If we want the robot to actually make a bed someone has like slept in, and not just like a cover is like slightly pulled down. It probably needs a lot more power to be able to fluff a giant duvet. From a modeling perspective, the robot has very limited context. It doesn't remember anything about what it has done so far, how it has failed, and things like that. So if we want a robot to navigate through like an entire home and clean it all up seamlessly, it'll likely need all this context. Okay, thanks for your attention and for the opportunity to share these with you. I'm happy to take any questions. Yeah.
Hi, can I ask a question? Hello?
Role of simulation could be here.
Oh, sorry.
Safety or kind of like figuring out what the robot can and cannot do, or do you see simulation having any role at all in this pipeline?
It's a good question. I guess there are like I think one obvious one, or like one that has been not obvious, but like something that has like already been started to be explored is like using simulation for evals. Not obvious, but something that has like started being explored. Yeah, so I think that's like a really great direction because I think it's really hard to get. So like basically all of the real world evals, if we're like being honest, like are somewhat like vibe based. And I think that's like an important component of like doing like real world eval. Like you have to go like take it to like random places and like actually just like see what it can do. But I think like in order to like really understand like certain things and to get like really statistically significant results, like we should probably use better methods for evaluating the models. I think that's one. I think in terms of safety, I think that's like a little bit difficult because like when you have a mobile manipulator, like you'll have to integrate that with like its sensors. Like so like in terms of like your situational awareness and like how much interact, like that's, I feel like that's a bit difficult. I also think that like being able to generate like programmatically generate like scenes for the robot to train in is like a really promising direction, but I think just now it seems maybe not like the most straightforward path towards like training these models for like many reasons.
Thank you. I think there was one more question on Zoom.
Okay.
Yeah.
Oh, yeah, I think reinforcement learning could definitely play a role in post-training, and like making the model more robust, adjusting strategies, making it faster, safer, for example, like if you're able to like detect that, you know, like yeah, I guess like we did like bump the robot a lot into like stuff that we shouldn't have. So I think like for example, if we have logged those things and being able to like teach the robot like don't do that, like that's like a really obvious like way I think it could help. In addition to like things like speed or even just like adapting, let's say like I think I guess I personally believe that you won't be able to zero shot everything. But if you can do a little bit of like online adaptation, I think that like would be really powerful.
Hello, can you hear me, Laura? Sorry.
Go ahead.
Yes, I had like maybe two questions. The first question is, you showcase an example when you try to make the model do a very difficult task with the towel. But are there any cases when you go about trying the model when you try to maybe do a task that is simple and you think it should be intuitive, but I couldn't do it? And the second question that I have is about vibe-based evaluations, because I think this is typically how you go about evaluating a new model. You see that you take the new model and see what is it able to do. Do you have like a protocol to come up with the tasks or things to make it do, or it's like totally random? Because this is something that I wonder a lot. Like, what is a good way to figure out what a new model that you try can actually do?
Yeah, I think okay. So to address your first question about like tasks that seem easy, but then it's not able to do. I think usually, like this has definitely happened before. I think, for example, like you see this like utensil holder. Like we had a task of like picking up like spatulas or wooden spoons and then putting them into the utensil holder. And like that seems like pretty easy. But because of like, the wrist cameras like here, you won't like be able to see like the bottom of the utensil like inserting into the utensil holder. So I think like usually if it's like a simple task that we expect to work, there's usually some kind of like somewhat straightforward explanation for why that is. Like I think like, yeah, if we just like observe like, oh, this isn't working, just like thinking about, like usually it's like an observability problem, or like maybe you just don't have enough data or something like that. Yeah, I think that, so to address your first question. And then for in terms of like vibe-based evaluations, I guess like that's something that I also like, this really made me reflect on, and I don't really know if there's like a good like way to structure evaluations other than like, I think one key thing is like having rich enough and realistic enough environments, and then like letting the model kind of like show you what it can do, I think is like kind of like an interesting way to go about it. Because it's like if you like designed, oh, I had these like 5 tasks that I collected a lot of data for, and I'm gonna like set up the scene so that is like gonna like I have an expectation of like what the robot's gonna do, then it's like doesn't really have an opportunity to like go beyond that. But I think of course like we also should do like evals of like tasks that we know are in the data and like make sure that those work. But in terms of like going beyond that and doing more like open-ended stuff, I don't know. I think certainly having like richer, more realistic environments will just like kind of like force you into that more interesting regime. And then also like, yeah, I think the more interaction and realistic you can make the situation, I think like the more you'll like learn.
Right, we probably.
Okay, yeah, we can do more. Yeah, we can ask
Take the
for-
rest of the questions offline.
Okay.
Let's thank Laura again. Did you get the Zoom link by any chance? So you just need,
Probably should mute and then
exactly, just join the Zoom, mute and share your slides there. And then this will be the camera and the sound for the online stream.
post camera and
Oh, yeah, you just share your slides here?
yeah. It's fine. Yeah?
Yeah.
Okay, sounds good. Then and
Oops.
it's the last one. Maybe that's it. First or second. Okay.
The map will work with your session.
Yeah, I'll briefly introduce you.
Yeah,
Yeah,
sure.
alright.
Go ahead.
All right, it's my pleasure to introduce our final speaker for this workshop, Elahe. Elahe is the head of AI research at Wave and adjunct professor at TUE. And I think Wave and the work that Elahe is probably going to talk about today perfectly embodies the spirit of this workshop, which is general policies in the wild. I think Wave has deployed like many end-to-end policies like in the wild on real roads. So yeah, I'm very excited to see what we have to talk about.
Thank you. Good afternoon, everyone. Hopefully it's you have still energy to listen. That's why I added a lot of video for looking at like make it a little bit more interesting. And thanks to the organizer for the invitation and nice intro. Today I'm going to talk about the frontiers in embedded AI. Specifically, I am going to focus on the role of language and word models and see how these foundation models are going to enable a scalable and safe autonomy. On average, every US person is driver waste over 50 hours a year stuck in traffic. It's basically more than 2 days per year. It's just wasted. And then on top of this inefficiency, there is human cost to it also. Like every year we are losing over 1.3 million people on road with the accidents, and 1 out of 2 are the pedestrians or cyclists. And then this is the road accidents are cause number 1 for losing the young lives. And adding to that, it's like basically every 24 seconds someone is killed and a lot of injury is happening. And this is not becoming a technical challenge anymore. It is also kind of like a moral aspect to it. Now the question is that wouldn't this will be nicer if we had some self-driving cars that they have superhumans and they can avoid all these car accidents on the road. This has been the dream for over decades now, but we haven't, it hasn't been materialized yet, and we are not there yet. The question is why? Let's discuss that. The autonomy has turned out to be far harder than it has been predicted by everyone. And the reason for that is that people started to focusing so much on perception and forgot about the basically decision-making process is beyond perception. And then many of these L4 level robotaxis are working in a small pockets, but they cannot generalize beyond that specific roads and cities. Testing is slow. It's basically expensive and hard to repeat these situations. That's another factor. And then on top of everything, now regulators and the policymakers and the public trust is another blocker. And all of this is slowing down the whole progress. This is what we call it AV 1.0, basically the conventional approach that the industry started working on it. As you see, it's a heavy modular stack with a lot of sensor input and a lot of perception tasks that's predefined, and all the connections are created already, and then the planning. And then if you look at the graph, you can see there is the map down there. And that's basically referring to high definition map, which on its own, it's another challenge for AI. And we know that this is very expensive to create because it depends on a lot of label data. And every piece of that system is creates some friction. HD maps, as I mentioned, is really hard to maintain updated. And creating them is another challenge. Even after they are created, updating them and keep them updated, it's another challenge. And then if you want to go from one geo to another geographic place and make your model works, you need to change your planner. If you want to change the sensors, reduce the number of cameras or add some new sensor stack and so on, then you need to rewrite the whole stack again. And if you want to deploy on a new platform, on a new embodiment, on a new car, good luck, you need to redo everything from scratch again. And on contrast, when we need to, on contracts, this is basically what we are trying to hope and curate the words towards what we believe it should look like, but the word is not that. And we need systems that they're working with the words that it is the way right now. In meantime, there has been a huge advancement in the domain of cognitive science. And with AI, we have seen that many tasks have been suppressed the human level capabilities, including solving math problems and coding. And we believe embodiment or embodied AI is the next big frontier. Embodied AI is about grounding the intelligence in the real world. The machines can act, can see and reason in the real world environment in our messy world, and driving is one of the ideal proving ground for that. Here is an example that you can see how complex the environment could be. Like many things are happening here, pulling out, pulling in on your line, and then jaywalkers passing. And this is what we believe, that the autonomous driving is not just a robotic or engineering task. It's more an AI, fundamental AI problem. And the core difficulty, as I mentioned, and perception is on the decision-making. And decision-making in a complex, uncertain, and interactive environment. And driving is not an aesthetic task. It's social, it's a dynamic, and requires forward reasoning about knowing how everybody is going to interact with this world. The key challenge in deploying autonomous driving at a scale is adaptability, safety, and trust. If you cannot, basically these three factors are interlinked and they are not separated. And you cannot make trustable systems if they are not safe. And you cannot assure safety if your systems are not adaptable and cannot adapt to the ever-changing environment. And what unlocks the autonomy at a scale is the generalization power. And if your system breaks down every time that it sees a new condition and environment, then it's not an intelligent system. What we are trying to do at Wave is building a system that doesn't just work here, but work everywhere. It's generalizable at a scale. Here are our system driving from London to many other places, to San Francisco, Germany, and so on. With AV 2.0, which is our approach at Wave, we are moving away from rules and from maps. And we are going towards end-to-end AI journalists. And here we see the system that adapting to the new environment without any need of re-engineering. You can see all different types of road layouts and different cities. What I refer to as AV 2.0 is has a very sharp contrast with AV 1.0. And what is the difference? We don't have this predefined engineered stack of perception and planning anymore. And it's just replaced by a giant neural network. And this is much leaner and flexible and is sensor agnostic, and there is no need for HD maps. We don't need these highly definition maps. And it can integrate to any type of embodiment in different vehicle types. The solution that we offer, it works across different vehicles, cities, and without HD maps, as I mentioned, and it can scale from different type of autonomy, from providing the driver assistant features like automatic emergency braking to full driverless, basically eyes off, hands off, and one architecture for many different embodiments, for different features and different capabilities. Here's a concrete example that a system can generalize and adapt very quickly to new environment. Our system have been trained on UK data for a long time. And when we started our operation in US, the zero-shot generalization is the first bar. And you can see with only 500 hours of incremental data, we have like 40x improvement in our metrics. And that shows how these models can very quickly learn and adapt to new systems, and they are very data efficient. What's even fascinating more for me is that this data is not just helping to get better at that specific geo, it also helps with the third geo location. Here we added that data from US with the UK data, and you can see how much improvement in the Germany, the third city, is provided. It's basically showing that adaptation accelerates here, and each a new geography makes the next one easier. And this is showing how data efficiency and these learning systems that are designed to be efficient and more generalizable are having this compounding generalization. Our aim is one AI model going to 500 cities. We have already with zero training on the data from those cities across 3 continents. And towards our goal, we already have done roadshows in 90 different cities, and we are going to see some of the demonstrations. But basically, what is behind this is Wave Foundation model that it's a general purpose driving intelligence that make this scalability at global scale and adapting to unfamiliar roads and traffics and weather condition, and beyond that, like the social norms of different cities, different countries are very different. Here the example, I will keep it short, but you can watch the full video on our website and our YouTube channel, but you can see all these places that our main data is coming from highway and urban areas, how much they can basically go to villages, roads, different parts of continent and cities. Like the diversity that you are seeing is huge here. But if we were going with a modular system, rule-based system, for each of these changes, we needed to add some new rules to be able to our system to work in. For the interest of time, I'm going to just keep it short. As I mentioned, the core of this is a foundation model. And like GPT is for language, this is also for autonomy. And it's a shared representation across different sensor stack and different modalities. And it can output different modalities as needed for different downstream tasks. The foundation model is pre-trained on petabyte of data of our internal fleet partners and some of the external data that we acquired over the time. And what we have seen in the language is that this foundation model enables generalization and bring similar to them. These are also bring different capabilities for new embodiment and environments. But embedded AI has its own challenges, and it's much harder than building a chatbot because you cannot just simply scrape the internet for driving data. There are so many rare and edge cases that and safety critical events that you need to make sure that your systems are robust to them. And you need on-policy driving data, and you need to be able to evaluate those systems and make them safe, repeatable, and covering long tail scenarios. This is where language comes into play, because LLMs already encode a surprisingly good amount of knowledge about driving rules, road behaviors, and human interaction. And also, in addition to that, because they know these rules and social norms and strategies, they can guide us towards more reasonable and interpretable systems. And we can use them for planning, for perception, and for different counterfactual tests, basically. We started with Lingo 1, which was a vision question answering system, and basically bringing this interpretability to these black box systems, and showing the very short video to the system and asking what it perceives or what is the plan for next and so on. And it could answer in a very human-friendly language. And which this one enabling auditing and also debugging and explanation for the system. Here are a few examples. You can see I'm staying stop because the lead vehicle in front of me. And then as soon as it changes, the description, also the explanation of that is changing. And there are more. And then, the lingo one was the first step towards this explanation. And when you were asking question like what did the car stop for, it could reason and show also the video doesn't work, sorry. Okay, it could basically refer to the segment, like saying that, okay, the white car is in front of me, and refer to that with the segmentation map on top of that. As I explained, Lingo 1 was just a backseat driver. It just could look at the scene. Somebody else was in charge on the driver's seat and just explain what it perceives from the action and the plans. But we took this one further ahead. And with vision language action models, we tried to connect all these things together, perception, reasoning, and control through the language. And now the model can both act and explain its own action. This is Lingo 2 at in the public roads. It's the first time having such a system in public roads in London. And as you can see, the system online can make its own action and based on the language can explain it and describe its own planning. The longer video is also on our website. Why this matters, like why we are using the language model. There is a very famous saying that is that language, like a paragraph of text, may be worth 1,000 videos and frames. And language gives us this powerful path for data efficiency. Basically, one of the aspects we can solve is the data efficiency, and another aspect is the interpretability and explainability of these models. And language also, like a future direction that we are already studying is that can bring us, like many of our systems, the current system are reactive systems. They are basically working in system 1. And Daniel Kahneman has this theory that our brain has a dual system memory. You have system 1, reactive, system 2 is a slow, and it's forward thinking. And now we are working that planning the interaction with the words that humans also interacting needs this forward thinking. And we need the system that be more reactive as well as a slow thinker. But on the other side, there are some rare dangerous data and scenarios that are hard to collect data for. And we need to evaluate our system on those scenarios to be able to deploy these models, because we are going to save lives, not put them on more risk. And now, for this reason, the generative word models are coming to play and becoming essential. Basically, with word model, we can bridge the gap between what is the real data collected and what these long tail scenarios we need to test our model on. And this, for getting there, word models enable us to have dynamic and controllable diverse scenario generation and test our system, verify our system. We have started this topic by the first autonomous generative models that it's called Gaia 1. It was a discrete video model trained with next token prediction. It was promising, and at the time it was one of the kind, but we wanted more than that. We wanted more controllability and diversity in the scenario generation. That's why we evolved from Gaia 1 to Gaia 2, that extending this diversity and controllability. Both these models are receiving few seconds of short context of video. The first row is Gaia 1, the other two are Gaia 2. And you can see that Gaia 2 is generating images, generating smoother motions, and it's also, you can see it's multi-camera, higher resolution, and way more temporal and spatial consistency. You can see these are the back cameras. When you are passing one of the buildings or cars, they are appearing in the other cameras. At its core, Gaia 1 has a video tokenizer. And why we are using that? Because it compresses the raw pixels into structured tokens and making the sequence modeling tractable and ensuring that the model learns meaningful representations. Within this latent space, then Gaia 2 is a diffusion model conditioned on camera geometry, because we need to generate across different sensor rigs, because we want to go from one platform, one car type to another, a different embodiment, basically. Cuboids to control the other dynamic road users, and action vectors to control the ego vehicle itself, and metadata, which is useful: time of day, weather, road types, and so on. And then the Gaia 2 supports two high-level modes. Scene generation from scratch. Basically, you can see the first row, and it can be conditioned on metadata, layout, or intent, or the second mode, which is autoregressive rollout, predicting plausible futures from a given context. And it needs to keep it coherent with this past context. It can also simulate a longer sequence than it was trained on. And all these come together, it adds flexibility and makes it invaluable for both policy learning and evaluation of such systems. This is Gaia 2, which supports a full surround video generation. It has 360 view around the ego vehicle. It's a global geographic diversity, it's multi-platform simulation, and it's fine-grained controllability over agent and lightning layout and so on. Every recorded scenario that we have, there are only one countless potential of many different scenarios possible on the real life. And that being said, leaving a gap in our edge cases and our data distribution. And Gaia 2 helps us to close this gap with augmenting and extending our data set. And how it's done, it's basically through simulating new, with the controllable conditions, simulating new environment. For example, here, going from one geo to another, different road types, and also different time of day. Here is a concrete example of how we can use this at a scale. The first row is the generic data, is the normal data, and then the rest of the rows are generated data, basically from the same row. Here, the action is overtaking a bus, and this is very rare. You can take it to different type of rows and different time of day, and even you can go to. This is another example for the same thing. The first row is sorry. Yeah, the first row is the actual data, and the action is starting from a red light. And you can generate many of these other examples from it. And now you can go also from US to UK and different condition, urban to suburban, and so on. Gaia can generate safety critical conditions, which is for autonomous driving and evaluation is very critical. It's very crucial. One of them is these pre-collision scenarios. It's near misses, near accidents, basically. They are very safety critical, and you cannot even afford to have these scenarios on road and test the models for that, because it puts everybody at risk. And we can generate now these near misses and test our models on those data. Another example is emergency braking. Here you can see we didn't have such a data in our corpus, but still the model learns how to basically interact with the conditioning that we have. And it makes the surrounding kind of that it's plausible, this action. We have some other obstacle, any type of vehicle in front of the road, and we need to do the emergency braking. Another class of these long tail events are these aggressive cut-ins. This could be from, it's one of those rare cases. It could be from both sides or one side, but these are very dangerous. And you can see that with conditioning that we have, and the conditioning you can see below is for the second example, that from both sides we can control and create that scenario. And also now we can do counterfactuals. Basically, if the model having a higher speed, what would be happening? And you can see even the risk, the hazard lights of the bus is turning to the red in action to that. This is generated, that's the original data. This is another counterfactual examples, and now you can see if the speed is extended, how the model is going to react to that. Yet another one, very quickly now here, the left one is, the model is running on the original road, sorry. And now here you can basically force it to change the lane and go to the sidewalk. And then another controllability that we have is that we can convert all these video streams that the data we have data for into embedded space, and conditioning on this embedded space, we can create thousands of variation of that scenario in different places, in different conditions, in different sensor stacks, different any kind of like controllability that you want. You can just we are using our in-house driving model for that, embedding a space, and each of them you can see how semantically meaningful are clustered around each other. Gaia also can generate reactive dynamic scenes. You can see here, it is very interesting example that if we are forcing the ego vehicle to go to the wrong lane, how the other car is reacting to that. It's taking the right action. It's basically going and trying to bypass the car. We can push models also into out of distribution. We never had such a system. Now we can basically drive in the bush and then test the models in here. We can make it extreme even, something that maybe right now is not possible, but you can see the other car on the road is continue its own path, and even on the back camera you can see them. Here the car is coming, as soon as we are going on the back side you can see, and it can drive into the ocean and beach. And now we are expanding this Gaia to even bring more value of data out, basically, from a single view clip. This is the original data, and now we can generate multiple view of that data. And all these spatiotemporal consistency across these different viewpoints and cameras are preserved here. Even we can now condition our models on LiDAR data and create RGB scenario for that. Now let's take one step back again and see if stepping back, this embodied AI won't successful just by being a fascinating technology on its own. It needs to be integrated to this dynamic and messy world, ever-changing world that we are interacting and living in. It should be scalable as a business for people to have that in hand and earn trust from public and policymakers and meet all the safety expectations and add real value for the life of people. That's why we are looking for superhuman power in the driving. This is the bar, and it's very high, but we are trying to solve that. And these shifts are happening already, are in motion. The industry is moving very fast. These are very recent news from our company that with OEM, we are partnering with Nissan, and they're going to use a Wave AI driver system in their stack. And also NVIDIA is considering the investment in the next series. And that being said, we are expanding, hiring, and if you're interested, please reach out. And I'm going to take the moment. This is very interesting. All the weird scenarios that a model can come across. This is London, and you can see that this was US, like all different, very weird situation that you can come across. And this is the power of generalization of this foundation model. They can generalize to different scenarios. And if they were rule-based, how they could make reasoning around this not driving there. And now this goose even is more interesting, like the car knows it should stop and then start again as soon as it's deciding to move. Yeah, thank you a lot. I like to keep the conversation going on. If you're interested, just reach out to me or check our website for the new rules.
Yeah, we have time for several questions.
Yeah, that was a nice talk. I'm curious about, you mentioned a couple of times that models seem to adapt efficiently to different cities. And I'm curious what the mechanism by which that adaptation happens. Like, that's like fine-tuning of a pre-trained model, or that's there's something else going on? Yeah.
There are multiple factors to this generalization and adaptability of the systems. One of them is coming at the core of it, which is the foundation model, is a general purpose representation learning that can understand from diverse set of data, even those data that we are not using for driving, maybe they are completely irrelevant for the task that we have at the end, but still they are encoding the knowledge of the world, how the world, dynamic world around us is evolving. And that's basically one of the factors. The other factor, of course, is coming from the recipe that we have for the fine-tuning that enables us to bring even more value of the data out and make these systems to reason better and generalize better and adapt to these unseen conditions.
I have two questions actually. The first one is about evaluation, and I guess like you're using variable for evaluations. Like how much does it correlate to the real world, and like in the end, how do you do some sort of A/B testing in the real world? And the second question is about the language following. I guess like Keynote is doing it's my understanding is that it's explaining what it's about to do, like why it's doing it, and producing the action. Do you think something like that can transfer to would improve the performance in the field of manipulation?
Very good questions. The first one about evaluations. we are using this synthetic data for evaluation and also for training. Like the safety critical data, as I mentioned, they are not available and nobody can afford to collect every possible condition and scenario on them and then train the models to be able to do emergency braking and so on. We are using for both cases. And about correlation, I cannot give the number, but I can give that already we are seeing very positive and even better than real data that we were using for evaluation. We are seeing improvement over that by using this synthetic data, because now there is more controllability. And then when the policy is changing, because these models are constantly changing, we are retraining and retesting, and that basically the data that we have getting off policy, and then but with the synthetic data we can keep it on policy and test and keep the correlation higher than the actual using actual data. And what was the second question? Sorry.
You think that if we get something like Robo to the Robo manipulation, whether you think it's going to improve the performance?
It will. I believe that language has a lot of knowledge about the world already. And as I mentioned, something that with language you can explain, you might need a lot of demonstration with the robot to enable the robot to understand the condition. And even then could overfit to those. But when the other factor is that the brain is a multimodal system, and these modalities are kind of complement each other. They are bringing different aspects of abstraction and representation learning and how they are all interacting and working together to make this generalization better. Because the end goal is generalization everywhere and for any condition. And to get there, the more modality we are using, the more scalable and data efficient and faster we can get there.
You mentioned on-policy data as important kind of for training. So driving, you kind of need a simulator if you want to do on-policy training, right? It's very hard to do on road. Do you think these kind of Gaia models or so are going to be useful for like kind of this kind of on-policy training? So kind of the concern I see is that there are big diffusion models, right? With like multi-resolution sensor that might be kind of too slow to do on-policy training, and I think that there's a way to kind of get around this problem.
That's a very good question. We are working on multiple aspects of bringing this efficiency into these models and use them for, you can call it a closed loop simulator. Put the models and they can interact within this, like two agents. One is the world model, the other one is the policy, the driving agent interact with that world. And that being said, we are working on something that making it interactive and efficient, and we had some progress already, and in-house we are using, but it's not public yet, unfortunately.
Thank you.
No problem.
Yeah, thank you very much. I want to ask about the safety regards. Is it kind of like uncertainty that you have like perception that and you have uncertainty or reliability that that's how safety now is considered in maybe, or there is another way?
Safety for evaluation could be based on the fidelity of the action and how risky it is. But also we have the safety subsystem, which if you see, it's a parallel system. Maybe I can already switch to that slide. And that, as you mentioned, it has been working on different possible safety map. This one. And this is how the system, when it's interacting in the real world, can be assured that it's safe and it cannot get into a hazard condition. But for evaluation, we have so many other things to test on. This is just a system in parallel trained, and it's part of this system for deployment.
Actually, I have a question about labels and also question. You mentioned a few times that you don't really need them in your pipeline specifically.
But like what we often find also with other labels than just maps, it's like really hard to do evaluation without them, or even like verifying the motion plan like you have a system for. Can you maybe like give a bit of intuition what labels are still required than just like trajectories, and like maybe how you can do verification either during evaluation or on the fly to kind of like achieve this?
I'm not sure that the HTMaps always are needed. I'm coming from HTMap background also prior to Wave, but my belief is that HTMaps are not needed and they have their own challenges and a lot of other problems. But when it comes to evaluating our systems, is basically different scenarios. You can have you can use a lot of perception tasks if you are willing to, and you want to make sure that the systems are understanding the world as it is, for example, a pedestrian, a jaywalker, a cyclist, and so on. And then you can use those tests offline. But then a lot of other evaluation online being used, and that's, for example, an interactive world model can be used online, and a closed loop simulator that you can put the models, the same system that we have, this end-to-end sensor inputs are in, actions are out, and we are measuring the actions. And that's how, if the actions are verified and they are not dangerous with some of the other metrics, then that's how it's verified and evaluated.
Okay, I see, but like, you still need to have something like bounding boxes or so, or like, I meant the HTML more, whether you go off the road or not, or is there no explicit sort of representation of that at all in your testing pattern?
We have both. You can do without any of those label data. As I mentioned, just with the trajectory, you can still verify your system, how plausible those actions are. And the other one is that you can still test your system counterfactually, adding objects, removing objects, and see how these models are reacting to those changes in the world. And for that, you can basically make use of this privileged knowledge and some of the label data that you have.
Thank you.
Regarding the world model, the diagram, can you give us an intuition of the scale after which it actually starts to become useful? Like how much data you have to use to make a model that was useful for verification purposes or data innovation, or maybe that came with different scales? I'm not sure if I missed it in the presentation.
No, you didn't miss it. I had it, but I removed the slide. I wanted to show it, but I remember that I removed it. It's not hidden. The scale of data matters a lot. The size of model, I would say, matters, but more than that is the data quality that matters. And also for how long you are training. Like we moved out from autoregressive models to diffusion models, and we used a lot of like camera consistency. It brings another level of knowledge, that how consistent is information from one camera to another, spatial and the temporal, like backward in the time, and also across these different cameras. Those are enabled to models to be better. If I remember correctly, the compute cost compared to Gaia 1, we are using 4x the compute cost. And then the data is accordingly also like proportionally increased a lot here, and we trained for longer time.
So like is the work or like guide to train on a different subset of the data compared to the driver that being evaluated?
Repeat the question, please.
So like Gaia 2 is trained still on driving data, right?
Yeah.
Is it trained on a different subset of the driving data compared to the driver that is being evaluated, like the model that you're trying to evaluate with that?
It has some overlap, but it's not the full set. We have some data that we are not using for the fine-tuning our policy, and we have some data that we are using for policy, but we are not using for the world model training. And there is a subset of that that overlaps between the two stages.
Great, let's give Vladi one more round. Follow-up question.
Thank you. Thanks.
Right, I think that concludes our workshop. Thank you all for coming. Hi. Oh, yeah. Yeah, nice to meet you in person. Yeah.
Yeah, great presentations today, and it was like delightful. I had a question after like seeing a lot of the evaluation and people learning there. It seems like we're at this point where like the evals, like the average level is like a little harder than like where our models are, just,
Yeah.
like straight out of the box. And so like I was like in another like the eval and deploy room and people were like, oh, like without fine tuning it, like almost all the models they tried like didn't do very well on like some tasks they designed, and then even with fine tuning on like thousand demonstrations like pi, it's kind of well, but the other ones are still like at like 0, and so it's like not informative. So I'm kind of curious, like from your experience when people have been running their stuff, like do you feel like the RoboArena tasks are at a like easy enough difficulty that people can have like, you know, piecewise progress, or do you think it's like a lot of zeros, which makes like, I guess it's like hard because that means like there's more data sets or like post-training things to be given out before like these can be useful to people.
Yeah, I think that's a great question. I think with RoboArena, I feel like one thing people tend to do is that they want to come up with like interesting tasks.
Yeah.
And the interesting tasks tend to be harder tasks. Yeah. I think, you know, technically, there is some signal even in those tasks being gained, right? Like with the preference, like if one task, you know, if neither succeeded, but like one task made a better attempt or made more progress. I think though, like when, you know, when it is the case that you evaluate on a harder distribution of tasks, you are testing a different capability of policies, right? Like you're testing the capability of policies to still make progress, even though they can't succeed at the task. Versus, you know, if you got an easier task, then you're actually testing the capability of policies to complete the task. I think like, you know, both are useful capabilities. I think, yeah, if you were to sample like oversample harder tasks, which maybe a little bit is what's happening in RoboArena, you are testing the latter capability, like the ability to, you know, still make progress when the policy may not know what to do. I think also a function of it is the embodiment. I think it is the case right now that like current closed source generous policies trained on closed source data sets are actually good. Like a lot of the tasks that maybe we're commanding the robot to do in RoboArena can actually be solved. With like with the correct embodiment that was trained. I think what that means is that current like generalist policies still struggle to adapt to new embodiments. Like for example, the way we got a lot of our pi or a lot of the pi RoboArena policies, like the pi 0.5 droid policy, was to basically fine-tune the pi 0.5 model on the droid dataset. And in fact, I don't think pi collects data with that robot at all. So it's basically a brand new embodiment transfer.
So I mean, like, yeah, like testing things with pi, like on average, it's already kind of like a different one. Okay,
yeah,
that's interesting.
I think that actually explains a lot of maybe the less than expected performance of pi-based models, like on the Franco robots. Like yeah. So I think yeah, I guess I don't know if that's the question, but
Really like interesting because like my original intuition would be like, okay, let's say that I'm designing like a task like the oven towel thing, and then it's like, okay, like I'm down to help people out, and like I will collect a data set and just give it to you guys, like but then like for example, like would it be an interesting eval where like, because we have like data collection, like teleop capabilities too, and like what if we just like collect the data set of like a task that we're designing an eval for, just to see like, you know, can the models like, you know, with a little bit of context perform better? But then is that like I guess like I don't I haven't seen people like try like a lot of different evals like infrastructure to help people test in different ways. Like is releasing such a data set even useful to people trying out different models, or like because what Laura said, she was like, oh, even giving the examples didn't really work, and it's back to square one, which is like, okay, there's nothing I can help on the eval, so it's like you just go off and make your model general and more better.
Yeah, yeah, it's an interesting question.
As you mentioned, like, you know how you said like one thing was like the droid is like single arm, and if someone did release like more data sets out there that would help people generally move along. So I'm like kind of wondering, like, not that we can do like a huge like researchy data set, but I'm wondering if there's like some fine line like for evals, which is like, oh, like if I'm starting to do like hard kitchen tasks, but what if I gave people like a little more kitchen data? I'm wondering if that would be helpful to
Yeah, I think actually, definitely that could be the case. I think one way to test how good a generalist policy is like, maybe we're not at the point where generalist policy can zero shot do everything. I think we're definitely not at that point. But if a policy is such that in its generalist policy pre-training, it has learned great representations to the point where if you were to give it some small additional data set and fine-tune it, it learns very quickly or very data efficiently and can lead to really good performance. I think that's a good testament to the original generalist policy pre-training itself.
So it does reflect what
Yeah, and I think like a good example is actually in some of the RoboArena, or if you look at the RoboArena leaderboard right now, the leading policy is 0.5. And the main difference between this model and the other models is that it was pre-trained on a lot more robot data and on other internet data sources. And it was fine-tuned on the same droid data set that other models in the same leaderboard were fine-tuned on. So the fact that it does better then is only a function of its pre-trained, which is a good, again, testament to how good it is as a generalist policy. It's like, and that's you can sort of envision droid as your small data set that you collected to fine-tune on. So yeah, I think yeah, totally. That's a very valid way of getting signal for like how good the generalist policy is.
Okay, cool. Yeah, and we're still getting our RoboArena set up, but once we get like everything finished and up and running, we're like excited to try it out, and we'll like reach out and see how we can help get on board and stuff.
Yeah, sounds good. Yeah, excited to have you guys do that. Yeah.
Thank you so much. Yeah, and thank you for like hosting this room today.
Oh yeah. Nice seeing you.
I'm very sorry, but we need to probably empty the space.
Oh, okay,
yeah, we can probably, you can probably wrap it up. Is this yours? Or
it's Carl's laptop.
we can just